Buenos días, gracias por esperar estos minutos. Mi nombre es Pablo Agüero y voy a hacer la introducción de este webinar que se está titulado Bases del aislamiento sísmico y disipación suplemental de energía. Vale la pena mencionar que bueno, el ingeniero Barone va a hacer su presentación en inglés. Un par de anuncios antes de iniciar. Las personas que están usando nombres genéricos en el Zoom, por favor, cambiar a su nombre completo, nombre y apellido, para así poder extenderles el certificado de participación. Además, el ingeniero Barone va a hacer dos presentaciones, entonces, después de la primera, va a hacer una sesión de preguntas y respuestas. Entonces pueden ir escribiendo sus dudas o comentarios en el chat de Zoom. Entonces, bueno, procedemos a iniciar con esta introducción. Antes de cederle la palabra al ingeniero Barone, el LanammeUCR es una institución académica de investigación adscrita a la Escuela de Ingeniería Civil de la Universidad de Costa Rica. Es un laboratorio especializado en investigación, docencia y transferencia de tecnología en infraestructura civil, alineado con los tres pilares de la Universidad de Costa Rica. Es responsable de ejecutar las actividades de fiscalización, evaluación, actualización, asesoría técnica asignadas por la Ley 8114 para garantizar la calidad y eficiencia de la inversión pública en la red vial del país. El LANAME está dividido en una parte administrativa, sus laboratorios y tres programas, del cual voy a hablarles un poco del programa de ingeniería estructural, el cual tiene como objetivos contribuir al desarrollo de la ingeniería estructural en Costa Rica, fortalecer la posición de la universidad como institución académica de investigación mediante el apoyo a la docencia y la investigación que realiza la Escuela de Ingeniería Civil, y velar por las responsabilidades que le asigna la Ley 8114 y su reglamento en materia de infraestructura de puentes. Con respecto a esto último, de estas capacitaciones, webinars que realizamos, son parte de nuestras responsabilidades. En cuanto al programa de ingeniería estructural, actualmente está coordinado por el ingeniero Julian Trejos Villalobos, y el programa tiene dos unidades: la unidad de puentes, que también está coordinada por el ingeniero Trejos, y 7 profesionales que le dan apoyo. En cuanto a la unidad de estructuras, actualmente está apoyada por los profesores de la Escuela de Ingeniería Civil. Y si quieren más información al respecto del programa de la LANAME, de los otros programas, pueden ingresar a nuestras redes. Ahora, para ir entrando en materia con el webinar, repito el título: Bases del aislamiento sísmico y disipación suplemental de energía, impartido por el ingeniero Stefano Barone. Los objetivos son describir el concepto de aislamiento sísmico en la respuesta de estructuras ante los eventos, los terremotos, comparar el diseño de estructuras que incluyen y no incluyen aislamiento sísmico, y presentar aplicaciones y la variedad de dispositivos que funcionan como aisladores o disipadores de energía. Nuestro expositor, el ingeniero Barone, tiene una maestría en Ingeniería Sísmica y Sismología en la Escuela Universitaria Superior de Pavía, en Italia, y realizó, bueno, sus estudios de pregrado, tanto en la Universidad de Pavía como en la Universidad de Catania, en Italia. En cuanto a su experiencia profesional, tiene muchos años de trabajar para Freycinet en los departamentos de ventas, de diseño, investigación y desarrollo, todo relacionado con dispositivos sísmicos. Previamente estuvo en el departamento de escenarios de riesgo del Centro, que es una institución sin fines de lucro que se dedica a la investigación. Y sin más preámbulo, le cedo la palabra a Stefano para que nos dé las dos presentaciones que preparó. Muchas gracias, Stefano, por la oportunidad.
Thank you, Pablo, for the introduction. Really a pleasure for me to participate to this webinar Thanks to everyone who is attending this morning. Here it's afternoon in Italy. And yes, as Pablo mentioned, we will have two presentations. One is on, let's say, seismic isolation and energy dissipation concept. And at the end of this presentation, that will be approximately 40 minutes, there will be time, I guess, for questions that you can write on the chat. And then we will have the second part of the webinar that is more dedicated to seismic analysis of structures that are equipped with seismic protection devices. So type of analysis that we can do it, and as well some real cases, some real applications. So now I'm going to share my screen. Let me know, Pablo, if the presentation will be shared in the proper way.
Yeah, it is correct.
Okay, perfect. And what about if I use this visualization? You see the main screen?
No, right now we are watching the secondary screen.
Okay. So I put in the normal way. Okay. So the first presentation is basis of seismic isolation and energy dissipation. So we start with a, let's say, brief introduction. We all know, what are earthquakes and let's say, what is this phenomenon that we have to deal in many countries of the world, like Costa Rica and all the Central and South America. So we know that an earthquake is, let's say, a brittle failure of a fault that is, let's say, in the crust. This rupture typically happen suddenly, so without any, let's say, prediction, and this is the reason why it is impossible, at least up to today, to predict, let's say, the earthquakes. We can predict the intensity, but we cannot predict when they will happen. And this brittle failure is due to the accumulation of strain energy inside the ground that at some point is released, it's suddenly released because a rupture in the fault appear. And so when there is this rupture, this rupture will create the famous seismic waves, and these seismic waves will propagate inside the ground up to the ground level. And we know that the distance between the point where we measure the acceleration and the rupture of the fault is called the focal distance, while the distance, the projection of the distance in the horizontal direction is called epicentral distance. So if we have, as you can see here, a building or a structure that is fixed on the ground, the main question is, what does the structure do with the seismic energy? No, that's the main concept. And as you can see here, as you can imagine, if I have a structure that is fixed on the ground, during the vibration of the ground, the building will start to shake it. In this picture, we can see what really happened during an earthquake. As you already know, in the ground, we will have at a certain depth. This depends, of course, on the location where we are, but we have typically the bedrock. And so here you can see, for example, in a green line, a typical accelerogram that will appear, let's say, can be recorded at the bedrock level. But then, most of the time, it happens that between the ground level and the rock level, I have some additional layer of soft soil, and the consequence of a flexible soil is that the acceleration from the bedrock is amplified. So at the end, when we register the acceleration at the ground level, that is in this case the blue line, we can see that the earthquake, the original earthquake, that is, let's say, the green line, was already amplified before shaking the structure due to a soil amplification. In fact, this is called soil effect. Then there is also the topography, the topography effect that can amplify as well the seismic acceleration. So now the blue line, that is the earthquake, the accelerogram that is registered at the ground level, will start to shake our structure. That can be, let's say, a skyscraper, it could be a cable bridge, and so on. And the other amplification effect is that the accelerograms, that is at the base, that shake the structure at the base, typically it is amplified along the height of the structure. It is amplified by the structure itself, and it is the red line in this case. So we have a double amplification of acceleration. One comes from the ground flexibility, and the other one from the structure. Why? Because we will see this concept with a response spectrum. The concept is that typically or generally a building or a structure, if it has, let's say, a frequency, a period of vibration that is close to the frequency content of the earthquake, you have the famous resonance phenomenon. So anyway, so in this slide you can see that typically we have a certain level of acceleration at the bedrock, and then this acceleration is amplified by the ground if between the ground level and the bedrock level we have the presence of flexible soil. So in the end, the acceleration at the ground level is typically amplified by the soil. In fact, this is called the soil effect. Then, if we have a building or a structure that is fixed on the ground, this will be shaken by the earthquake, that is, in this case, the blue line. And during the shaking, the seismic acceleration at the ground, it is amplified along the height of the building, along the height of the structure, as you can see here in the red line. So we move from the green signal to the red signal, and this is because typically the structure amplify the seismic acceleration if it has a frequency or a period of vibration that is close to the frequency content of the earthquake. So in the end, we have a sort of resonance phenomenon. And here in this slide, you can see some catastrophic photos of, let's say, buildings, bridges that collapsed during an earthquake. So these are all unfortunately, famous examples of buildings or structures that were not designed properly against earthquake. So how we can design as a structural engineers buildings against earthquakes. So what are the seismic design approaches available nowadays? Here in this slide, I try to summarize the three strategies that we have. Here you can see imagine the lateral force displacement response of a building. So let's imagine to have a building and to do a sort of pushover, to push laterally the building and to monitor the base shear and the displacement, for example, of the roof. The first seismic design approach is to design the structure to behave completely elastic. So the concept of this design strategy is to increase the strength of the structure as much as possible so that during the design earthquake, the structure will behave completely elastic. And so this is the elastic approach. Then we have the second approach, that is the elastoplastic approach, that is, let's say, nowadays the most used method if we are, let's say, in a medium to high seismic region, like, for example, Costa Rica. This is called elastoplastic method. So with this method, actually, as you can see here, we can reduce the design shear force of the structure. So we can actually design the structure for a low level of shear force, But on the same time, we need to increase the ductility of the structure. Why? Because it is thanks to the ductility of the structure that we can dissipate the seismic energy that is introduced in the structure, and so we can reduce in the end the design shear force of the structure. So this is called the elastoplastic design. And of course, during an earthquake, we will have a ductile behavior. So it means that we will have damage in the structure. And then we have the third design approach that is called, let's say, the seismic design approach with the seismic isolators or dampers, where, as you can see here, now the structure, in this case a building, is protected in this case by seismic isolators, but it's the same with dampers. So the concept is now that we can reach two effects. The first one is that, as you can see here, of course here we don't have a number, but the concept is that compared to the elastic design and to the ductile design, we can reduce the design shear force of the building. So actually we can design the building or the structure, the bridge, for a low level of horizontal force, of seismic action. And the second is that we can have the advantage of the elastic design. What does it mean? It means that the structure during the design earthquake will behave completely elastic. So this means no damage during a seismic event. So now we will go a bit more in detail of each design strategy before reaching seismic isolation and dissipation. So elastic design, as I mentioned, is the first design approach. And as you can see here, we have imagined the seismic energy that comes from the ground during an earthquake and our structure. So in an elastic design, the seismic energy that shake the structure, it is, let's say, 95%, 98% restored by the structure to the ground. Why? Because the design is elastic, so the structure cannot dissipate any portion of this seismic energy. There is so only a very small amount of this seismic energy that is dissipated by an intrinsic damping of the structure. It is the famous 5% viscous damping of a reinforced concrete building or a 2% damping of a steel structure. But the majority of the energy is completely restored by the structure to the ground. And as I mentioned before, if we take a look to the lateral force displacement response of the structure will behave completely elastic. So what happened? What happened that, for example, here we can see that if this is the building, our building designed just for gravity load, if we apply a seismic action, this is typically the effect of the application of an earthquake. So actually we need to increase, as I mentioned before, the strength, the dimensions of the structural elements in order to resist elastically, without any damage, the seismic action. So if we go to the characteristics, to the main characteristics of this design strategy, first of all, the elastic design requires an important reinforce of the structure, big structural components. Of course, this is function of the type of structure and of the seismic zone. You can understand that the higher is the seismicity, the higher will be, let's say, the strength increment of all the structural elements. The second characteristics of this strategy is that the structure is elastic during an earthquake. So this means that during an earthquake, we don't have any damage. The third characteristic is, and this is linked to the first point, typically an elastic structure requires a high initial manufacturing cost. Because we need to increase the strength of the elements. If it is a reinforced concrete structure, we need to increase the quantity of reinforcement and so on. Of course, this is again function of the type of structure and the seismicity. So the question, after having analyzed the elastic design is how we can reduce the size of the structural components and how we can reduce the initial construction cost, because these two seems to be the critical point of the elastic design. And that's why it's many years that we have the ductile design. And why the ductile design is used a lot all over the world, because now, as you can see in this part of the picture, an important portion of the seismic energy is dissipated by the structure, and it is dissipated by plastic mechanisms that are, for example, the famous plastic hinges in columns, in beams, in walls. So as structural engineers, we allow the structure to dissipate the seismic energy in specific point of the structures, like, for example, the edges of beams and columns. And remember that when we say dissipation, dissipation means damage. In fact, now if we take a look at this picture, this is, for example, a structure, a building that was properly designed according to the plastic ductile behavior. So this is a building perfectly designed, but you can see, for example, it appears immediately that after the earthquake, we have damage in many structural elements. In this case, we have damage on the top of all the columns. And this is normal because, again, it is a ductile design. So if we go to the main characteristics of this design strategy, first of all, thanks to the dissipation of the seismic energy, we can reduce the design seismic force to be applied on the structure. And this is the reason why, thanks to the ductile design, and it is the first point, we can reduce the dimension of the structural components with respect to the elastic design. So we have solved the first critical point of the elastic design, to reduce the initial manufacturing cost of the structure. The second point is that during an earthquake, we have dissipation of seismic energy. So we allow structural damage. I would say also non-structural damage. As a consequence of this point, a ductile system typically is not serviceable after a seismic event. It cannot be used because you can understand here that we have damage. So before using the building after an earthquake, we need to retrofit the structure. And consequently, we have to take into account all the repairing costs of the structural and non-structural elements. So now, having analyzed a ductile system, the new question is how we can reduce the damage, so how we can reduce the seismic effects on the structure. And this is the reason why nowadays, I would say now it's more than 40-50 years that we can use this technology. Here we have the third design strategy, that is the one with seismic devices. So now, if we, in our structure, install some seismic devices, that could be an isolator, salt dampers, or a combination of the two, the concept is that now a big portion of the seismic energy is dissipated by these devices. So these devices are exactly designed to dissipate the seismic energy, while a very low percentage, a low portion of this seismic energy is dissipated by the structure. So now, if we take a look to the characteristics of this design strategy, the first point is that thanks to the energy dissipation that comes from the devices, we are able to reduce the seismic forces acting on the structure, so reducing initial manufacturing cost of the structure. The second point is that now we don't have any damage of the building, so it's because we can design the structure fully elastic. And for this reason, as a consequence, a protected structure with seismic devices can be immediately used after a seismic event. So these are the three main characteristics of of a structure that is equipped with seismic devices. In this list, in this slide, we can see a recap of all the seismic protection systems that nowadays are available in the market and that can be used by the structural engineers. And they are typically classified in three product family. Three product family. We have the active control system, the semi-active control system, and the passive control system. In this presentation, we will talk about the passive control system. Just a mention between what is the difference between an active and a passive control system. The difference is in the word, no? Active control system means that is a protection systems that need to be activated. It could be, the activation is of course automatic, but it needs to be activated during an earthquake. And this activation could come, for example, from electricity, from a battery system, and so on. While passive control systems are, let's say, devices, systems that are installed in the structure, and they don't need any, let's say, activation. They can work for any earthquake. So that's why they are called passive. And inside the passive control system, we have, let's say, all the seismic isolation system, energy dissipation, tuned mass damping, and rigid connection system. In particular, in each standard, depending on the standard that you use, but typically for each family of product, for each system, you will find a description. So, for example, what is a seismic isolation system? It is a system, as you can see here, that uncouples the structure from the ground excitation and protects it from damaging effects of earthquake ground motion. What is an energy dissipator? An energy dissipator provides additional damping to the structure in order to limit, to reduce the maximum response of the structures during an earthquake. And then we have the tuned mass damping that are essentially masses that are installed in the structure to vibrate with a contrary movement with respect to those of the structure, like, for example, the mass that is installed on the top of the Taipei building. And finally, we have the rigid connection system, also called lock-up devices or shock transmission unit, that are rigid connectors. So they are like a rigid link that they are used to connect 2 points of the structure very rigidly during an event that is characterized by a high velocity. So it could be an earthquake, it could be a wind load, it could be a breaking load. And then, for example, depending on the standard that we use, we have, for example, a dedicated chapter. No? So, for example, if we take a look to the American standard for building, so the ASHE 722, Chapter 17 is dedicated to seismic isolation system, and Chapter 18 is instead dedicated to energy dissipators. So, for example, in this slide, I want to show you very quickly some videos regarding the testing, of seismic devices. So, for example, here, seismic isolation system, we can see the testing of I don't know if you are more or less familiar with this type of products, but essentially, for example, we will see during the presentation, seismic isolators are devices that are very rigid in the vertical direction and very flexible in the horizontal direction, because they have, as mentioned before, they have the function to uncouple the building from the ground movement. No? So they are very flexible in the horizontal direction, and this is the reason why they are tested in the horizontal direction. So, for example, in this video, you can see So this was the horizontal dynamic test of a rubber isolator, and here you can see the same type of test, but for a friction pendulum isolator. but the concept is the same. It needs to be very flexible in the horizontal direction. And if we take a look to the dampers, to the energy dissipators, here you can see a fluid viscous damper. The function in this case is just to dissipate the energy through the viscosity of the silicone fluid that is used inside, so through to the viscosity of this special fluid. And again, you can see here a typical production test. So this was to show you how these devices works during an earthquake. Here in this slide we can see I show you a recap of the most important seismic isolation codes that are used all over the world. Here I show let's say the most important, but there are many additional, like the Turkish standard, the Chilean standard, and so on. But these are the main one, and it's interesting to observe, for example, that the EN 15229, this is the European standard for seismic devices. And of course, this standard is used in Europe, but I can tell you that it's a standard that is used also across abroad Europe. For example, it is used in New Zealand, it is used in Indonesia, in the Philippines. It is used as well in Central and South America. Why? Because it's a standard, for example, that covers all the seismic products that are available in the market, and also it contains design rules that can be used by the designers, and it is mandatory to be used by the manufacturer also. And so it's a standard that is used abroad Europe if the specific country does not have a specific standard for seismic isolation and dissipation, so it can be adopted. Here we have the ASHE, the 722 and the 4117. This is the American standard for buildings and also for the retrofit of the existing buildings. So it's a standard applicable in the United States, but again, it is a standard that it is used as well, for example, in Mexico or in Chile and so on. And finally, we have ASHTO, that is the Guide Specification for Seismic Isolation Design. This is a standard dedicated to infrastructures, so bridges, viaducts in the United States. But again, it is a standard that can be adopted in another country if that country does not have a specific standard. So, for example, ASHTO is used a lot in Mexico, in Costa Rica, in Chile. So that's why I wanted to show you this standard. Okay, now let's take a look to the let's say the performance-based design. The performance-based design is, let's say, the way how nowadays we design every structure. There could be a bridge, an hospital, a private apartment. So this is, for example, the structural performance table for a conventional design. So typically, if we have to design a building or a structure to resist an earthquake, what we do essentially is to consider different level of earthquakes. So in this case, you can see now the frequent earthquake, the design earthquake, the maximum considerable earthquake, so different earthquake intensity. And then we have different limit states, no? For example, we have the operational and the immediate occupancy limit states that are, let's say, service limit state. And then we have generally we have two ultimate limit states that are the life safety and the collapse prevention. So performance-based design means that we associate a specific limit state to a specific earthquake intensity. So this is the way how we design a conventional structure, no? And then, depending on the, let's say, on the importance of the building, when we perform the conventional design, we take into account the importance of the buildings. For example, if we take a look to the ASH, this table is taken from the American standard of buildings. In ASH, we have the so-called importance factor, while in ASTO or in the Eurocode, it is named in a different way. The concept is that depending on the importance of the building, I need to, let's say, change the performance of the building itself, of the structure itself. So, for example, if I have to design a structure with that is in class 1 or 2, so it means I don't know, a private condominium, no, a private apartment. What I will do in a conventional design is that I will design the structure with this performance. So for the maximum considerable earthquake, I will design the structure to prevent collapse. For the medium earthquake, I will design the structure to protect the lives. And for the frequent earthquakes, I will design the structure to, let's say, to allow the immediate occupancy after the seismic event. But what happens if, let's say, I increase the importance of the building? If I increase the importance of the structure, I have to increase the performances. Think about if I have to design now a suspended bridge or a skyscraper or an hospital. Now I have to shift the line, the inclined line on the left side of the table. What does it mean? It means that I have to increase the performance. So now, for example, if I have to design a buildings, an hospital, now for the maximum considerable earthquake, I want to, of course, to prevent collapse, but I want also to avoid any loss of life. And for the intermediate level earthquake, I want the immediate occupancy because, for example, the structure is an hospital, and so I want that my hospital after the earthquake can be used immediately. And of course, for the frequent earthquakes, for the low intensity earthquakes, I want that the structure can be used immediately without any activity after the earthquake. So now let's see what happens in case of an isolated building, or in general in case of a building that is seismically isolated. This table is taken again from the American standard for building, and for example, now we can see an interesting fact. The first one, we can see that typically an isolated building is designed with the maximum level of performances. So you can see now that for the maximum considerable earthquake, if the structure is isolated, we prevent collapse, we protect the life, but we are able to design the structure to be used immediately after a seismic event. And of course, for all the lower intensity earthquakes, we can satisfy the operational limit state. So the first important result is that if the structure is isolated, we can reach the maximum possible performance. And the second point, you can see here that now all the types of buildings are grouped in the same line. So whatever is your structure, a private apartment, a suspended bridge, an hospital, if the structure is isolated, we can design the structure with the same level of performance. In fact, in the American standard for building, but this is the same for all the standards, all the seismic codes, if the structure is isolated, the importance factor is kept equal to 1 for all risk categories. So it means now that we can design from the private apartment to the hospital with the same level of performance. And in fact, if we take a look to what the American standards say for isolated structure, this concept that is in the table is very clear also in the sentence, because we can read together ASHE 722 say that in general, isolated structures designed in accordance with the standard are expected to, first point, resist minor and moderate levels of earthquake ground motion without damage to structural elements, non-structural components, or building contents. So, by the way, another important point, you not only protect the structure from, let's say, structural damage, but with seismic isolation, you are able to protect also the non-structural components, and we will see why, and also the building content. So imagine, for example, if you have particular equipments that is installed in the structure. And the second characteristic is that an isolated structure is designed to resist major levels of earthquake ground motion without failure of the isolation system and without significant damage to structural elements, extensive damage to non-structural components, or major disruption to facility function. So now, in this video, we can see how a building with the same building with and without isolation will behave during an earthquake. So here you can see, for example, that typically a structure without isolation will start to deform during an earthquake, and here you can see that the deformation of the building along the height, the famous interstory drift, while the same structure isolated will behave in this way. So you can see now that the structure that is supported by the isolator during an earthquake will move like a rigid block, like a rigid body. And the main advantage of this is that if we take a look to the stories of the building, the relative deformation, the interstory drift, is reduced a lot. And this is the reason why during an earthquake we reduce damage to the non-structural components. In this video is interesting because it shows you the numerical comparison of a tower, a normal tower, so designed with a ductile plastic design, and the same tower designed with a system of fluid damper that protects the structure from the earthquake, no? And this video shows a comparison. So, for example, on the left, you can see always the original hospital with the conventional ductile design. And on the right side, you can see the building, and you can see that at the mid-story, in the central story, you have some yellow line, and these are the fluid damper that are installed in diagonal braces. So if we take a look to the video, you can see, for example, already that the structure that is not protected will deform a lot, so will oscillate with a higher amplitude, while the one that is protected, no. Why? Because the dampers allows to reduce the acceleration and displacement of the structure. This is the main advantage of using fluid dampers. In this picture, for example, in this video, you can see, for example, on the vertical axis, we have the second story drift over the time of the earthquake. The blue line is the hospital protected. The red one is the original hospital. So you can see how the fluid damper can reduce the story drift. And you can see also another advantage. If I have a structure that is designed for ductility, so to be damaged during an earthquake, typically after the earthquake you have some permanent deformation in the structures, like a residual drift. While if the structure is protected, at the end of the earthquake you don't have any residual deformation, because the structure will behave elastically if protected. If we move on with the video, for example, now you can see very interesting a plot on the vertical axis. We have the flexural moment against the rotation of the shear wall that is installed at the base of the two buildings. And we can see that if the structure is protected, the blue line, the wall will behave elastically, while in the other case, it will start to enter in the plastic range, so it will start to be damaged. And finally, if we take a look, for example, to the acceleration on the last floor of the building, so on the left side, we have the acceleration over the time, and on the right side, we have the floor acceleration against the period. You can see the beneficial effect of using a fluid damper. In other words, a fluid damper is capable to reduce also the accelerations at the last floor of the building. Here, for example, we can see a real application. This is an hospital designed and built in Martinique. And here you can see how the finite element model of the building. So this is how the building will behave during an earthquake. So it will move, as you can see, like a rigid block. It's like uncoupled from the ground. And here you can see, for example, some construction phases. No? So on the top right, you can see, for example, the construction of the foundation with the installation, in this case, of the rubber isolators, and on the bottom you can see the final construction of the building. You can see that at the basement of the building, where we have the isolation level, you can see that there is a sort of gap between the ground and the building, and this is typical of isolated building, because as we saw before, the building during an earthquake has to move, no? Because it is isolated, and so you need to create a gap all around the building that is essentially equal to the displacement demand of the isolator. So now we go a bit on the definition of the response spectrum. I will go a bit fast on this part because I imagine that you are all familiar with the concept of response spectrum, but I just want to tell you that the response spectrum it's a powerful tool that is used not only for conventional building, but also for isolated building. And I can tell you that for an isolated structure, let's say the concept of single degree of freedom, and so the concept of response spectrum is very important, very interesting. Because why? Because typically, if the structure, if the isolated structure it's well designed, during an earthquake it behaves essentially like a single degree of freedom system. So imagine that an isolated structure during an earthquake, it's like a mass that is supported by a certain spring with a certain damping, no? So it's a concept that is very, very useful, and it is used, for example, for you can easily pre-design an isolated structure with a response spectrum. And in this slide, for example, we can see, let's say, the main concept of seismic isolation and energy dissipation. On the left side, we have the response spectrum, in this case, the uniform acceleration response spectrum. Typically, whatever is the seismic code that you use, the response spectrum can be defined for different level of damping. For example, in this case, it is plotted from 2% to 30%. And on the right side, we have the typical shape of a displacement response spectrum, no? Again, for different level of damping. So the first concept that we can see is that if in some way we increase the damping in the structure, we can see that the effect of damping is to decrease acceleration and mainly displacement. And this is one concept of seismic isolation and energy dissipation. So the first concept is to introduce damping, in this case with specific devices that could be isolators or dampers, in order to decrease acceleration and displacement. And the second concept of seismic isolation, that is let's say the fundamental one, is to increase the period of vibration of the structure. While you can clearly see in the response acceleration spectrum. If we are able to increase the period of the structure, for example, from, in this case, I don't know, 0.5 second to 2 seconds, you can see that we can reduce a lot the acceleration on the structure. So this is the first main concept of seismic isolation, to increase the period of vibration, because in this way we can decrease the level of acceleration acting in the structure. But what happens in terms of displacement? If we increase the period of vibration, it means that we are making the structure more flexible. So we are increasing the displacement of the structure. But pay attention that this increase of this displacement increase is not a displacement of increase of the structure, but it is the displacement of the isolators. And the isolators are in fact designed to, let's say, to sustain a certain level of deformation. So it's an increase of displacement of the isolators, not of the structure. We can see that an important concept is that typically when we design an isolated structure, the isolators not only increase the period of vibration of the structure, but they will also introduce a certain level of damping in the structure. It's very difficult, or I would say it's very unrare to let's say, to install an isolator without any damping capacity. Why? Because damping helps to reduce the acceleration, but also to reduce the displacement of the isolator. This is very important because, for example, if you imagine that we are in a very high seismic area, like for example Costa Rica or like for example Turkey, if I increase the period of vibration from, I don't know, 0.5 second to 2 seconds, 3 seconds, and I don't introduce any level of damping in the isolation system, it could happen that the displacement of the isolator will be of 1 meter, 2 meters, so it will be too high that make the isolator impossible to be designed and to be manufactured. So that's why if we are, let's say, in a medium to high seismic area, we also introduce a certain level of damping, because by introducing the damping, we are also, the increase of the damping will help the isolator to reduce their deformation. And so in the end, to have isolators that are smaller and at the end that can be produced, that can be designed and manufactured. So these are the two main concepts. One is increasing the period of vibration, and the second one is to increase the damping. And again, as I mentioned before, damping could be increased, could be introduced through the isolator, or could be introduced by a specific device like the energy dissipator, the dampers. So here you can see, for example, what happens if I have a fixed base structure, a structure without isolation. This is the typical behavior during an earthquake, so the structure will start to deform, and typically a structure that is designed without damping, for example, will have this, let's say, this level of acceleration. If we introduce a seismic isolation, this is now the new behavior of the structure, so you can see that the isolator will deform during an earthquake, but the building will behave like a rigid block. So now the deformation of the building is reduced almost to zero. And so we shift the structure from this performance point to this performance point. So in fact, this is, let's say, the typical building that is a good candidate for seismic isolation. So if the structure has a period that is in the region of maximum amplification of the seismic acceleration, and an isolated structure. An isolated structure typically has a period that goes from 2 seconds to 4, 5, 6 seconds. This is the typical isolation period range. Here I show you, let's say, a nice example. It's more an academic example, but that show you how, let's say, a structure can be designed with different solution. Every time that we want to design a structure, we can think to different strategies. The final answer will be to find a solution that is a good balance, no, between the cost of the solution itself and the performances. So, for example, in this case, in this example, we have a portal frame, classic portal frame. Let's assume, for example, with a period of 1 second and a damping of 5%. And the same portal frame, for portal frame, it's analyzed with a diagonal damper and with an isolated, a base isolation level, as well with a damper. So now let's assume to take all these structures and to shake them with the same earthquake. In this case, the El Centro accelerogram. So you can see, for example, on the left side we have the spectral acceleration, the acceleration spectrum, and on the right side the displacement spectrum of the El Centro earthquake that is plotted. It's calculated for different level of damping, no? From 5%, for example, to 20%. So taking a look to the spectrum and having the let's say our initial structure, we can understand where we are in terms of response of the structure, depending on the system that we use. For example, if we consider the original portal frame, so the frame with a period of 1 second and a damping of 5%, you can see that this type of structure, I mean, I can design the portal frame without any protection system, but I need to consider, let's say, in this case, a spectral acceleration of about 0.5 G. So you can see that the structure, the normal portal frame, need to be designed with an important seismic action. Now, what happens if I introduce a diagonal damper, for example, with a 20% with a 20% damping? The viscous damper has the characteristics to increase the damping, but it does not change the stiffness of the system. So imagine that now the period is 1 second and the damping is increased to 20%. So you can see now that looking at the acceleration, we move from point A to point B. So you can see that by increasing the damping from 5% to 20%, we can design the structure for a level of acceleration that is about 0.2, 0.3 G, that is almost 50% of the design acceleration of the normal portal frame. And now, so it seems that solution B is more, let's say, optimal with respect to the normal portal frame. Now, what happens if we, instead of introducing a viscous damper, we introduce an hysteretic steel damper? An hysteretic damper, imagine that is a damper that has the capacity to increase the damping, for example, again, 20% like the viscous damper, but it also introduces stiffness in the system. So in this case, imagine that the period is shifted from 1 second to 0.5 seconds. So now we move from point B to point C. So you can see now that even if we are introduced 20% of damping in the system, actually we need to design the structure for a level of acceleration that is even higher of the original portal frame. So you can understand that for this structure and for this type of earthquake, a solution with an hysteretic damper is not convenient, because I am introducing a damper, but I have to design my structure for a high level of structure with respect to the case of the normal portal frame. So the normal portal frame, of course, is more convenient. And now, what happened point D? That is this one, if we introduce just a steel brace, just a diagonal brace without any damper. This is the worst possible solution, because now the damping is not modified, it's always 5%, like the original portal frame, but we are reducing the period of vibration to 0.5 seconds. So I can do this, but now my portal frame has to be designed for a level of acceleration that is almost equal to 1g. So it means that this solution, for sure, it's the most unfavorable for this structure. And now, what happens if we take a look to the isolated solutions? For example, point E represents a portal frame with isolators at the basement without any modification of the damping. This is, as I mentioned before, a more academic example, because typically an isolators also introduce a certain level of damping. But let's assume, just to increase the period, in this case to 2 seconds, without modifying the damping on the system. So the damping is kept to 5%. You can see that by increasing the period, by doubling the period from 1 second to 2 seconds, we are able to reduce the acceleration from 0.5 g to almost 0.2 g. So you can see how much beneficial is the period elongation, so the seismic isolation effect. And now, the last point that is also interesting, what happens if we introduce also an isolator with a certain level of damping, for example, 20%. We can see an interesting thing. We can see that in terms of acceleration, we move from point E to point F. So you can see that if I have a damping of 5% or a damping of 20%, the acceleration reduction is not so important. Why? Because thanks to the period elongation, in this case 2 seconds, we are already in a range of periods where the earthquake does not excitate too much my structure. So if I have 5%, 10%, 50% or 20% damping, more or less the response is the same in terms of acceleration. Yes, there is a small reduction, but it's negligible. The main advantage of introducing the damping, as I mentioned before, is in the displacement of the isolator, because now, without damping, I would need to design the isolator, for example, for a displacement level of 200 millimeters. While with a 20% damping, now I can design the isolator with a displacement of 120 millimeters. So in the end, this means a smaller device that is also more economical. So the concept is that by introducing a certain level of damping, we will help the isolators in reducing their response. And here in this slide, you can see a sort of recap of where the typical positioning of the seismic devices. No? So for example, in buildings, typically the isolators are installed at the basement. Sometimes they are installed at the level 0, sometimes they are installed at the level 1, level +1, but in general they are installed at the base. If we have a flexible building, another solution could be, instead of isolating the structure, could be to install some diagonal braces, no? In the structure equipped, and the diagonal is equipped with, it could be equipped with a viscous damper or an static damper. In case of bridges and viaducts, typically the devices are installed between the pier and the deck, and sometimes they can also be installed between the abutments and the deck. And here, going to the conclusion of this presentation, you can see, for example, an interesting study that was done by the University of Tokyo. This is the paper that you can freely download from the website. And actually, what they did was to analyze 5 different types of structures with different structural configuration. No? So, for example, here you have a steel moment frame and a steel frame with diagonals designed for ductility. And then we have 3 different systems designed with different, let's say, type of devices. No? So, for example, in this case, the structure is equipped with viscous dampers that are the green line. In this case, the structure is isolated at the base. And finally, a structure that is isolated at the base with, let's say, a system of diagonal braces. And what they did was to calculate for each of these structures different parameters that are listed here. So, for example, the first parameter that they calculated is the loss due to damage. So, everything is expressed, of course, in Japanese yen, but it's important to, let's say, to observe the magnitude, no? So, the loss due to damage is the cost that the money that you have to spend after an earthquake. If you have damage, of course, in the structure. So you can see that if the structure is designed as a ductile system, as I mentioned at the beginning of this presentation, ductile system, it means damage during an earthquake. And in fact, you can see what could be, let's say, the money, no? The level of money that you have to spend due to the damage, due to the seismic damage. While if we start to protect our structure with specific devices, you can see that we can reduce a lot this cost, almost to zero, exactly to zero. So zero, it means that after an earthquake, during the earthquake, the structure will not suffer any damage. So after the earthquake, you don't have any retrofitting cost. Then another interesting parameter that we should take into account when we design a structure is the recovery time or the downtime period. Because, of course, if the structure is damaged during an earthquake, after the earthquake, I cannot use the structure for a certain period because I have to retrofit the structure. You can see that, for example, for a ductile system, depending on the level of the damage that you have, the downtime period could be very important. Here, in this case, is up to 26 months, so it's more than 2 years. While if the structure is protected, the recovery time could be reduced to, in this case, 8 months, 3 months, and exactly to zero. So zero, it means that the structure can be used immediately after the design earthquake. Another important parameter is, for example, the loss due to the recovery time. So how much I have to spend if the structure is closed, it's stopped after the earthquake. For example, think about that your structure is an hospital. If the hospital cannot be used, then I have to spend other money, for example, to move all the people from one hospital to the other one. These are called indirect costs or costs due to the recovery time. And again, if the structure is damaged, this cost could be very important. If the structure is in some way protected, also this cost could be reduced up to exactly zero. Another interesting parameter that they have assessed is the initial construction cost. So, for example, here we can see that this is just a case. Of course, this is an example, and it's not always the same because it depends on the type of structure, it depends on the seismicity and so on. But, for example, here we can see that whatever is the system that we use, more or less the initial construction cost is the same in this case. It could happen that if the structure is protected in some way, it could happen that, I would say that most of the time no, but it could happen in few times that the structure isolated or protected could be a bit more expensive than the conventional structure, but you can appreciate that the order of magnitude is the same. In other cases, the initial construction cost of an isolated structure could be much, much lower than a conventional structure. And then we have the second parameter, the total loss. This is just the sum of the two, no? The sum of the loss due to damage and the loss due to the recovery time. So again, here you can see that if the structure is designed for ductility, this cost could be very, very, very high. And finally, the most important parameter is the ratio between the total loss and the initial construction cost. Here you can really appreciate the advantage of protecting a structure with a certain protection system. In fact, if I design the structure for ductility, this ratio could be very high. Here we range between 60% and 50%. So it means that after the design earthquake, I have to spend, let's say, a quantity of money that is almost equal to 50% or 60% of constructing a new building. So this is the reason why it happens that if a structure designed for ductility it is damaged by the maximum considerable earthquake, it could be more convenient to demolish the building and to build it again, because the cost that you have to keep is to retrofit the building, it's very, very high. While if the structure is protected, this ratio could be very low and exactly equal to zero. So it means that you don't have to spend anything after the earthquake. So the same results is shown here in terms of, let's say, amount of money. The black line is the sum of the two losses, loss due to damage and loss due to the recovery time, to the downtime. So the black line is the total loss, and you can see that by starting to protect the structure, we can reduce the black line. So we can reduce the total loss almost to exactly zero. And going to the end of the presentation, here you can see, for example, two empirical plots that can help a designer, a structural engineer, to select among the different seismic devices that are available in the market. So these are empirical plots that are based on the experience, but they give an idea on how what device you can use for your structure. So for example, here we have on the horizontal axis the ratio between the ground acceleration and the acceleration of the isolated building. So what is this ratio? It is actually the filter that is given by the isolation system. For example, a ratio of 5, it means that the acceleration that we have in the isolated buildings is 1/5 of the acceleration of the grounds, or in other words, the acceleration of the isolated building is reduced by 5 times the one of the ground. And so it's let's say a measure of the isolation level. On the vertical axis, we have the seismic hazard, the seismic intensity from moderate to high to very high. And here we have the different devices that you can have in the market. So for example, the HDRB, that are the high damping rubber bearings, the LRB and PS, that are the lead rubber bearings and the friction isolators, and the FD, that are, for example, the fluid damper. So from this, let's say from this plot, you can see, for example, that if I am if I'm designing a building in a low to moderate seismic region, with a high damping rubber bearing, I can reach whatever is the isolation level. So a high damping rubber bearing will be enough for the majority of my structure. But if I start to increase the seismicity, so I am now in a high seismic region, now you can see that I will need to use, most probably I will need to use lead rubber bearings or pendulum system. Why? Because these devices have high damping capacity. So I am in a high seismic region, so I need to dissipate on a high level of seismic energy, and therefore I cannot use an HDRB that has a limited damping capacity. And what happens if I am in a very high seismic region, like for example New Zealand or Turkey? Now I have to dissipate a lot of seismic energy, and so this is the reason why it could happen that I need to use both isolators and dampers, because I have to dissipate a lot of seismic energy, and fluid damper, for example, are devices that are designed to dissipate the energy. The main goal of a damper is to dissipate energy. Another interesting plot, for example, is on the right. Here now you have on the horizontal axis the isolation system period, that is typically a parameter that is selected by the designer. And on the vertical axis you have the displacement of the isolator. So this is an interesting plot because, for example, this plot can be read in three different ways. For example, if I take a look only on the isolation system period, I can see, for example, that if I decide to design my structure with an isolation period that is between, I don't know, 1.5 seconds to 3 seconds almost, this means that probably I can find a solution with HDRB, with LRB, as well with pendulum. So I can find a solution with different products. But if I increase the period of vibration beyond 3 seconds, for example, 3.5, 4, 5, 6 seconds, now most probably I have to use a pendulum system. Why? Because with a pendulum system I can increase the flexibility by just increasing the radius of curvature of the isolator. While with the rubber devices, beyond 3.5 seconds, it's very difficult to increase the period because I cannot increase too much the flexibility of a rubber isolator. Another way to read this plot is to take a look to the vertical axis, the displacement of the isolator. If I look to the vertical axis, I can see, for example, that if from the seismic analysis, I get a displacement that is between 10 centimeters and 30, 40 centimeters, again, probably I can find a solution with HDRB, with LRB, or with pendulum. But if I increase the displacement of the isolators beyond 30, 40 centimeters, for example, 60 centimeters, or even 1 meter, you can see that now I am forced to use a pendulum system, a friction isolator. Why? Because with the friction isolator, I can just increase the diameter of the sliding plate in order to accommodate the displacement. While with the rubber isolator, I should increase the height, I should increase the rubber diameter, and up to a certain point, the rubber isolator will become too big, so it will be impossible to produce it. And finally, if I combine the vertical axis and the horizontal axis, so by having information on the displacement of the isolator and the isolation period, now I can identify exactly my solution. And finally, in this slide, we can see, let's say, a recap of all the products that are available in the market. Here I show you very, very quickly, because it is not the intent of this seminar, the ISO-SISM range, that are, let's say, all the seismic devices that can be designed and produced by Freyssinet. They, as you can see here, they include all the isolation products, so the seismic isolator, HDRB, lead rubber bearing, pendulum system. Then we have the family of dissipators. They could be fluid viscous damper, they could be displacement dependent device, or hysteretic damper, or pre-stressed damping. Then we have the shock transmission unit, so the rigid connector, and of course the seismic joint, because as you know, if we are isolating a bridge, then we need to install also a seismic joint that has to follow the movement of the isolator. So with this presentation, we are a bit in delay, but let's say we end the first part of the presentation. So before introducing the second part, that is more on the seismic analysis, we can answer to some question that you may have. Okay, Pablo is asking, what is the useful life of the devices shown in the videos? Let's say that the useful life of a device depends on the type of device, and of course on the environment, so where the device is installed. So if it is installed under a bridge, or if it is inside a building, and so on, I would say that on average we go from let's say, a minimum of 40 years to 60 years. So this is typically the nominal life. So nominal life, it means that is a period in which, by just doing a regular inspection and maintenance of the device can work safely, so it does not need to be replaced. After this period, we suggest to take one devices to test it, to see how the performance changed over the years, and to understand if we need to replace the devices or if the device can be still used in the building. Okay, if I don't know if there are other questions on this part.
No more questions for the moment.
Okay. So we can proceed with the second part. Okay, basics of seismic analysis. Let's share again the screen. Let me know, Pablo, again if you can see the screen.
Yes, we can.
Okay, perfect. So this second part of the presentation is more on basics of seismic analysis with the seismic protection system. So how to analyze a structure where I have to introduce isolators or dampers. This is the presentation outline. So we have, I think, almost 30 minutes. So I hope to cover all the topics. So we start with the typical seismic protection design workflow. Then we will see different seismic methods, seismic analysis methods that can be used for isolated structures. And finally, I think this is the most important part, we will see some seismic isolation design example. So here you can see, let's say, here I don't want to spend too much time, but this is the typical flow chart that is used when we design a structure with some protection systems. No, of course, it's a general flow chart that could change also depending on the country, depending on the, let's say the typical philosophy that is used in a specific country. But generally speaking, when we have to design a structure with seismic devices, we let's say we have the structural design. The structural design is typically done by the design engineer. And then if we have to implement a seismic protection strategy, typically, let's say the design engineer work with the seismic engineer. Again, this is, let's say, a general flow chart. It depends also on the country, because there are countries in which there is a distinction between a seismic engineer and design engineer, and other countries where the two figures are merged together. But let's say that if I have to, let's say, define a seismic protection strategy, I have to do the structural design, but also the seismic design. So once I select the seismic protection strategy, for example, I want to design the structure with the isolators, then I perform a preliminary seismic analysis. And this preliminary seismic analysis, it's typically competence of the seismic engineer. Then, by performing the preliminary seismic analysis, then we, let's say, we get the preliminary design of the seismic devices, so the preliminary characteristics of the seismic device. And typically, this is done, again, by a seismic device engineer. Again, this depends on, let's say, on the country. For example, there are countries in which, in a design company, for example, there are engineers that are more specialized in the design, in the determination of the characteristics of the seismic isolators. In other countries or in other design company, the structural engineer is also a seismic engineer and is also expert on designing the devices. So just to tell you that the preliminary design of the seismic protection system, it is done by the seismic device engineer. And so once the preliminary characteristics of the devices are determined, then we can perform a complete detailed seismic analysis with the seismic devices. And this activity, it is done again in combination by the seismic engineer and the design engineer. And then if, let's say, the solution that we find is not, let's say, compliant with the performance that we want, here this red arrow is just to show you that we have to do, and this is typically what we do, we need to do some iterations in order to find the optimal solution. So yes, exactly. So in the end of the seismic analysis, if we found a solution that is okay in terms of performance of the building, we can specify the final design and specification of the products. If not, we will have to go back to the previous step. Okay, so what are the different methods of analysis that we can use? Let's assume that we want to design an isolated building, no? An isolated building, how we can think the structure in terms of modeling. Let's imagine that if I have a building isolated, I have my isolators at the base that typically they have a non-linear behavior. This is the typical force displacement response of an isolator. And then we have the superstructure. If the superstructure is isolated, like in this case, during an earthquake, it behaves elastically. So it means that I can imagine the superstructure with a linear behavior, so a linear stiffness and a linear damping. So how can I let's say, model this system, this building? In a simplified, because here we are talking about simplified analysis method, we can reduce our system to a single degree of freedom system, like I mentioned before, where we have a certain mass, and this mass is typically the mass of the superstructure, that is supported by a certain stiffness and with a certain damping, no? So this is what we actually do with the simplified analysis method. So we reduce our system, our 3D system, to a single degree of freedom system, where at the basement we have an effective linear stiffness that represents the stiffness of the isolator with an effective equivalent viscous damping. And this is, as I mentioned to you, the single degree of freedom system. So, for example, what happens if I have a bridge? If I have let's assume that you have a bridge, 2 piers, 2 abutments, and the deck is isolated. So the bridge is isolated. So this is the typical behavior of the isolator. So the isolator will have a nonlinear behavior. And then I have the substructure. Typically, if the structure is, if the bridge is isolated, I design the abutments and the piers to behave elastically. So for the substructure, I can consider to have a linear stiffness and a linear damping. Again, if I want to preliminary analyze my isolated bridge with a simplified method, what I do is to represent. This is actually my bridge, the model of the bridge, no? Where in every support I have a stiffness and a damping that is a combination of the isolator and the supporting system. And then I can reduce my global system again to a single degree of freedom system with a certain effective linear stiffness and effective equivalent damping. So the strategy is the same, to reduce my building to a single degree of freedom system with certain characteristics. So now we will see the main steps to, let's say, to analyze a building, to analyze an isolated bridge and to reduce it with a single degree of freedom system. And you can see from this flow chart that it can be easily implemented in a simple Excel file. So the first step is to define the bridge properties, no? So I need to know the number of supports, for example, the number of isolator per support. So in this case, we are considering lead rubber bearings, but it could be a different device. We need to know approximately what is the weight of the deck. We need to know also, we need to have an estimation of the participating weight of the pier. This is function can be determined depending on the shape of the pier. And we need to have an estimation also of the substructure stiffness that in an initial phase could be neglected. Then the second step will be to determine, of course, the seismic hazard criteria, so to characterize the seismicity of the site, essentially the spectral acceleration, the acceleration spectrum and the displacement spectrum for different level of damping. Then I need to, let's say, select the initial basic parameters of my isolators. In case of a lead rubber bearings, I need to know, let's say I need to select, for example, from a catalog, the characteristic strength and the post-yield stiffness. These are the two main parameters that characterize a lead rubber bearing. Then step 4, as we saw before, we have a system of isolators that are supported by the pier. So I need to calculate the effective stiffness of the combined pier and isolation system. And to do this, I have just, we can use this simple equation where we have the effective stiffness of at a single, for each support. The effective stiffness at support J is simple equal to a coefficient alpha times the stiffness of the substructure divided by 1 plus alpha. And what is alpha? Alpha is just depending on the properties of the isolators that I have selected, the stiffness of the substructure, and the displacement of the system. Here, it's where we need to do a first assumption, because the effective stiffness of a nonlinear system is function of the displacement, but I don't know the displacement of the isolator. So as a first trial, I need to guess what is, I need to assume what is the displacement of the system, of the combined pier and isolation system. So I do this assumption, that is the first iteration, and then knowing the displacement, I can calculate the effective stiffness at each support, and I can simply calculate the total effective stiffness. That is a sum of the stiffness of all the effective stiffness in all the supports, because they work in parallel. Then, knowing the effective stiffness, I can calculate, and having assumed the initial displacement of the isolator, I can calculate the displacement having assumed the displacement of the system, combination of the pier and the isolation system, I can calculate the displacement of the isolator, and consequently, I can calculate the stiffness, the effective stiffness of the isolator. After this, knowing the displacement of the isolator, I can calculate the displacement of the substructure by simply reducing by difference, the displacement of the system minus the displacement of the isolator will be the displacement of the substructure. Why this calculation? Because the substructure and the isolator work as in series, they are a system in series. So knowing the displacement of the isolator, I can calculate the displacement of the substructure, and then I can finally calculate the period, the effective period of the system, and for this I just need to know the weight of the structure and the total effective stiffness, and I can also calculate the equivalent damping ratio of the isolation system. By knowing the period and by knowing the damping, I can enter in my acceleration spectrum and displacement spectrum, and I can calculate the acceleration and the displacement of the isolation system. If this displacement, and this is typically what happens, if the displacement that I get is different from the one that I have used in the step before, I need to repeat, I need to do a second iteration and repeat all the steps. Typically in 2-3 iterations, I reach the full convergence. No? So, for example, this is a case study. No? Let's imagine that we have a bridge with a superstructure that is supported by 2 abutments and a pier. The abutments are typically very rigid, so we can assume that the lateral stiffness is like 10,000 kilonewton per millimeter, just to say that they are very rigid. The pier, we can calculate the lateral stiffness of the pier, depending on the height, depending on the section. And we can calculate also the weight of the superstructure. So now let's imagine that we want to isolate our deck with 2 friction isolators at each support, 2 pendulum systems. The pendulum system you can see here, it is made by, it's the one that we saw in the video at the beginning, so it's made by 2 sliding plates. So once, if you imagine to deform it laterally, this is the typical horizontal force displacement response of the friction isolator. So actually, the friction isolator, it's locked up to the friction force, that is simply the friction coefficient times the vertical load. Once the earthquake action exceeds the friction force, the isolator will start to displace, will start to deform with a stiffness that is simply the ratio of the vertical load over R. Over R is the radius of curvature of the isolator. So what we have to do is actually let's say this picture. This picture is actually taken from Ashton. So imagine that we have our deck that is supported by an isolator that is supported by a pier. So the isolator is characterized by a certain force displacement loop. Our substructure is characterized by a linear behavior. Why linear behavior? Because if I am isolating the structure, I want that the pier will behave elastically during an earthquake. And so in the end, the system isolator plus pier plus supporting pier, these 2 systems are in series, so I can calculate the combined effective response of the system. The 2 systems are in series, so it means that the stiffness is the inverse of the stiffness is equal to the sum of the inverse of the 2 systems. And so what I have to do with the procedure that we saw in this slide is to calculate at each step the displacement of the system. From the displacement of the system that is guessed at the beginning, I can calculate the displacement of the isolator, I can calculate the displacement of the substructure, and I can calculate consequently the stiffness. So here, for example, you can see a simple spreadsheet Excel file that you can easily implement in your computer in order to calculate the response of a bridge, an isolated bridge, with a simplified method. So, of course, we need to introduce the seismicity of the system. We need to introduce the characteristics of the pendulum. So, in this case, if we want to use a pendulum, the 2 main parameters that we need to specify is the friction coefficient and the radius of curvature. So, in this case, 5% friction and the radius of curvature. And then here you can see, for example, general structural information, so information related to the weight. And as I mentioned before, for example, for each support, here we have abutment 1, pier 1, and abutment 2. This is exactly we are analyzing exactly this structure. So what we have to do is to calculate for each position, so for each support, we can calculate the weight that is actually acting on its support. This is an input data. And then we can calculate the friction, the QD of the isolator, that is the friction force, and the lateral stiffness. And again, we can immediately calculate this parameter because the QD is just the friction coefficient that we selected, we assumed, times the vertical load that we know. And the lateral stiffness is just the ratio between the vertical load over the radius of curvature. That again is an input parameter. So we can immediately calculate the characteristics of the isolator at each support. Consequently, having assumed the displacement, because as I mentioned before, we don't know at the beginning what is the displacement of the isolation of the system isolator plus pier, but we need to know this displacement because the stiffness is function of the displacement. So we assume a certain level of displacement, and we can calculate immediately what is, of course, the stiffness of the substructure can be derived for the abutments and for the pier, depending on the height and the shape of the building, or of the pier, sorry. So having assumed the displacement of the system, we can calculate immediately the coefficient alpha at each support. We can calculate the effective stiffness of each support, the combination of isolators and the pier. Then we can calculate the displacement of the isolator. We can calculate the effective stiffness of the isolator. We can calculate the displacement of the substructure from the displacement of the isolator, and consequently we can calculate also the force that is acting in the substructure. And then we can, with this parameter, we can calculate, these are necessary to calculate the damping at each support. So in the end, by doing this activity, this calculation for each position, then we can calculate the total stiffness of the system, that is 4.04, and we can calculate the effective period by entering in the spectrum. Then with this parameter, combining this parameter, we can calculate the equivalent viscous damping ratio of the system, that in this case is 24.2%. Consequently, we can calculate the scaling factor of the spectrum, or the damping factor, and finally, we can calculate the displacement of the system. If this displacement is equal to the displacement of the previous step, then we can stop, let's say, the iteration. Otherwise, we need to use this displacement and to repeat all the calculation. So once we reach the final solution, so we know that the final displacement is, in this case, 198 millimeters, then we can, with this final displacement, we can calculate all the final characteristics of the isolator. And then, having the final characteristics of the isolator, for example, we can introduce the parameters in a software, in a finite element software. An important thing is that when we analyze a bridge, but it's the same for a building, imagine that, for example, this picture is taken by Ashto. If we imagine to apply the earthquake in the longitudinal direction, our single isolator will have not only a longitudinal displacement, but will have also a transversal displacement. And again, if I apply the earthquake in the transversal direction, my isolator will deform in both horizontal, longitudinal, and transversal direction. So this is, let's say, the famous 100%, 30% rule that is given in most of the standard, like, for example, ASHTO or the Eurocode, that essentially will tell you that if I want to combine the effect of the earthquake in the two directions, I can take 100% in one direction and I combine it with the 30% of the effect when the earthquake is applied in the other direction. The other method that we can do to analyze a structure is the response spectrum method. With the response spectrum method, what we do is to model the entire bridge. This is the same bridge that we analyzed before with the, let's say, with the Excel file, no? So now with the response spectrum method, we have to model the entire 3D building in my software. And here you can see we need to define the characteristics, the link properties of the isolator, no? Between the deck and the pier. And here, for example, you can see how the different mode of vibration of an isolated bridge. So typically, if the bridge is isolated, the first mode of vibration is purely a translational mode. In this case, it's a transversal direction mode. The second mode is a pure longitudinal mode. Then, of course, you have a certain torsional mode, and finally, you have a local mode. For example, in this case, it's a local vibration mode of the deck. Here, you can see, I will go very, very fast. This is taken again from ASTRO. If we want to perform a response spectrum method, the concept is that, and this is clear from this slide, of course, not all when I analyze my structure, not all the modes of vibration are isolated modes, no? So for example, in this case, mode 1, mode 2, and mode 3 are isolation mode. What does it mean, isolation mode? It means that they are modes of vibration in which the isolators are deforming. But for example, mode 4 is not an isolated mode, it's a local deck bending mode of vibration. In fact, it has, for example, a period of 0.5 seconds. So what does it mean? It means that the software, typically, depending on the modes of vibration, will use a different level of damping, and so will modify the spectrum with different level of damping. So for example, if this is the so-called composite spectrum for isolated bridge. Essentially, for all the modes of vibration where let's say the isolators are deforming, so they are isolated modes, the software will use the damping of the isolation system. While for all the modes of vibration where the isolators are not involved, that are, let's say, the structural modes, like for example, the modes of vibration of the deck, then the software will use a spectrum with no damping, or just with the elastic damping of 5%. So this is the way how the spectrum is used in a response spectrum analysis method. And for example, this is the, let's say, hybrid spectrum of the bridge. In this case, we had a period of vibration of 2.5 seconds. And so, for example, ASTRO tells you that for periods of vibrations that are higher than 80% of the period of vibration, so in this case 2 seconds, we need to use the damping of the isolation system. For all the other modes of vibration, we don't have to introduce any damping because the isolators are not moving. So for example, here we can see the typical response, no? The mode of vibration of a deck that is isolated. And we can see an interesting thing. And this is the reason why at the beginning of this second presentation, I told you that the single degree of freedom system is a powerful tool to preliminary analyze an isolated structure. In fact, you can see that by having implemented our bridge in our model, now we get a displacement of the isolator that is actually close to 200 millimeters. But if I compare the displacement obtained with the response spectrum at each support with the displacement at each support obtained with the simple Excel spreadsheet, you can see that we have a difference between 3 and 4%. So you can see how much the single degree of freedom system analysis can predict very well the final response of the bridge. And so this tool can be used as a preliminary tool for the seismic analysis, for the seismic design of an isolated bridge and as well of an isolated building. And finally, we go to the final analysis method that we can use, that is the more complex, the more, let's say, advanced one that we can use, that is the nonlinear time history analysis. So with the nonlinear time history analysis, actually what we do is to use in the seismic analysis the accelerogram. So now the seismic action is not represented by the spectrum, but it is represented by the accelerogram. So by real earthquakes. They can be real earthquake, they can be artificial earthquake, synthetic earthquake. And here I just want to show you that when we use accelerograms, why there is this comparison between spectrum and accelerogram. Actually, these irregular lines are the acceleration spectrum of this accelerogram. So this just to show you, maybe you are already familiar, that when we use acceleograms, of course, the acceleograms that we use in the analysis, they need to be coherent with the seismicity. And how we check with this coherence? We check this coherence by overlapping the spectrum of the accelerogram with the target one. So in the end, we need to select or to modify the accelerogram so that their spectrum is compatible, is close enough to the design spectrum, to the target spectrum. So for example, these are the acceleograms, the original acceleograms, and you can see that the irregular lines are let's say much different, much far away from the design spectrum. By scaling the spectrum, so what we do is to modify the accelerogram so that in the end their spectrum, that is the red line, it's very close to the black line, that in this case is the target spectrum. Of course, when we perform a time history analysis, let's say the most complete analysis is to apply two different acceleograms in the two horizontal directions, and also the accelerogram in the vertical direction, because the earthquake is also acting in the vertical direction. So typically we have three components for the acceleograms. And also, when we perform a time history analysis, typically before the application of the acceleograms, we apply the vertical loads, the dead loads, with a ramp function. This is typically useful. It is used because thanks to an initial ramp function, we apply the vertical loads in a very slow way, so that the mass of the bridge is not excited before the application of the earthquake. So, for example, this is the typical result that we can see from a time history analysis. So, with a time history analysis, we can see really how, in this case, the bridge, the deck is deforming during the earthquake. So, it's a real time history analysis where we can calculate the real dynamic response of the bridge. So this is the typical result that we can get from a time history analysis. And finally, if we take a look to the response of the link of the isolator, this is the typical response that we can see. So for example, the blue line is the response that you get from a classic response spectrum analysis. If you perform a time history, you will get a response like this. The difference between this plot and this plot is that if I apply the accelerogram only in one direction, of course, I cannot see the effect of the earthquakes that is applied in the two directions. And so in the end, I will see the response of the isolator that looks in this way. But if I apply the acceleograms in the two horizontal directions, then I can see that how I can really appreciate the real response of the isolator. For example, this is a bridge, a real bridge. It's a truss bridge a truss rod bridge that was isolated in a new truss bridge isolated in Indonesia is the Sewampu Bridge. This truss bridge is completely isolated at each support with the friction isolator. Here, for example, you can see the numerical response of the isolator for different accelegrams. And here you can see the experimental response, so the real response of the devices that were, in this case, were tested in Italy. Here again, the concept of spectrum. Remember that if I have a certain, let's say, design spectrum, I can use accelegrams, but then depending on the standard, for example, the American standard tell you that between, in a certain period of range, in this case from 0.2 to 1.5 the period of the isolation system. So in this range, I need to use accelegrams so that the average response spectrum of all the accelegrams matches the design one. So for example, these are the original accelegrams called unscaled. Then I have to modify these accelegrams, and of course the software can do it automatically. I have to modify the accelegram so that in this specific range of period, the average of all the spectra, that is the red line, is at least equal to the design spectrum. So this is the concept of scaling the accelegrams to have a spectrum compatible accelegram. And so, for example, in the case of the Sewampu Bridge, we can analyze the response of the isolators, for example, at the abutments. The main advantage of the time history analysis is that I can, let's say, take a look to the time history of each response parameter of interest. For example, here I can see what is the variation of the vertical force acting on at the abutments on each devices during the time history. For example, this is an important information that is difficult to have with a response spectrum analysis. And it is an important information because, for example, the friction isolator cannot resist any tension force. So it has to be compressed during the earthquake. So with the time history analysis, I can check, for example, that during the earthquake, there is no instant where the compression force goes to zero. And as well, for example, if I take a look to the vertical force variation in the internal isolator, here again I can appreciate that the devices at the central piers are always compressed during the earthquake. Another example, for example, it's a private building. As I mentioned before, seismic isolation could be applied with the same performance to many types of structures. So it could be, we have example of seismic isolation of bridges, of private apartments, tanks, and so on. For example, this is a real case. It's a residential house. It's again an example of seismic isolation in Indonesia, where we have a high level of seismic intensity, and you can see that even a private house could be designed with seismic isolation. So in this case, the isolators were, of course, you need to locate the isolator under all the columns. In this case, we use the lead rubber bearings combined with post-tensioned slab. So at the basement of the building, we have a post-tensioned slab, and I will explain in a bit why a post-tensioned slab is a good solution that can be used in combination with seismic isolator. So the design concept, it's a simple two-story reinforced concrete structure. We have used the lead rubber bearings for seismic isolation. Why lead rubber bearings? Because in Indonesia, the level of earthquake is very important, so we need to dissipate an important amount of energy. And we have used also post-tensioned slab. As I mentioned to you before, why post-tensioned slab? First of all, because if I make the slab at the basement very rigid, the first advantage is that the tensioned slab will act as a rigid diaphragm above the isolation system. This is an important requirement every time that we have an isolation system. At the isolation level, we need to have a rigid diaphragm because this gives better dynamic behavior of the superstructure and allows to have an isolation system where all the isolator will work in parallel. And the second advantage of a PT slab, a post-tension slab, is that I can reduce the number of required isolators because I can make span more bigger, and therefore I can reduce the number of supporting columns and consequently the numbers of isolator. So the design milestone of these buildings that are typically all the steps that you need to follow, no, when designing, in this case, a building with an isolation system. First of all, you need to design, of course, your building for gravity loads, because in static condition, if you have or you don't have the isolator, the design, of course, will not change. So the first design milestone is to design the superstructure for the gravity load. Then once the structure is preliminary designed for the gravity load, then we need to design the preliminary design, the isolation system, the foundation, and also refine the design of the superstructure. And this can be done, for example, with an approximate method, like, for example, the equivalent lateral force method, that is a simplification of the response spectrum method. Then, once the structure is preliminary designed, also in terms of isolation system, foundation, and superstructure, then I can perform, for example, a full nonlinear time history analysis in order to assess finally all the real response of the structure. In this case, we have used the Indonesian standard and the American standard for building, that, as I mentioned to you, is not used only in the United States, but also in other countries, like, for example, Indonesia. So 3D nonlinear analysis, an important concept to underline is that when we introduce the parameters of the selected isolators, think about that the properties of the isolator are not fixed. They are variable, so they can change, and they can change for many reasons. They can change due to temperature effect, due to contamination, due to aging effect, production variability, and so on. So the main concept is that when the designer is analyzing the structure, it is good that the designer is, let's say, in contact with the manufacturer, because the manufacturer can give, depending on the isolator that is selected, the manufacturer can provide the tolerances on the parameters. And in fact, at the end, the designer needs to perform at least 3 types of analysis. One, it's called nominal bound analysis, so it's the red line, so it's an analysis with the nominal properties of the isolators. And then it has to perform a lower bound and an upper bound analysis. That are 2 types of analysis in which, essentially, in simple words, the properties of the isolators are reduced. So, for example, the strength and the stiffness are reduced. So, and this is the blue line. And then the upper bound analysis, that is the green line, where, let's say, the performance of the isolators are increased. So, for example, the characteristic strength is increased and also the stiffness is increased. So the designer will perform these 3 types of analysis to have a clear overview of what could be the response of the structure by taking into account the variations in the properties of the isolators. So, for example, these are the devices that were implemented in the building, and this is the testing of the devices, where you can see the horizontal force, horizontal displacement of the isolators. And this is, for example, the executive drawing of the design of the devices. As I mentioned to you, once we perform the time history analysis, we need to select a certain number of accelerograms, but then these accelerograms need to be factored, so they need to be modified, both the horizontal accelegrams and the vertical accelegrams, so that in the end the average of all the spectrum, that is the blue line, it's always let's say equal or higher the design spectrum, the target spectrum, that is the red one, for the period of interest. In this case, the period of interest was from 0.39 seconds to 2.1 seconds for the horizontal direction, and for the vertical direction, the period of interest was from 0.1 to 0.50 seconds. So it means that in this range, I need to use accelegrams where the average of all the spectra, that is the blue line, it's higher than the design spectrum, the target spectrum. And for example, each standard, in this case the American Standard for Building, typically gives you rules to define the period of interest in the horizontal and in the vertical direction. And then by applying the scaling factor, here we are. Here we have all the set of accelegrams that can be used in our analysis, the two horizontal components and the vertical component. So in the end, for example, once we have let's say, defined all the characteristics of the structure, we can, for example, in order to, let's say, validate the response of our building, so in order to check that in reality our building is behaving how, let's say, how expected. For example, we can think to model the frame, so each beam and columns with a fiber model, so we can implement exactly the nonlinear behavior of beam and column. So for example, here you can see the section of a column that is modeled with fibers, where we are, for example, modeling the concrete the behavior, no, the behavior of the confined concrete. We are modeling the behavior of the unconfined concrete. We are also modeling the behavior of the steel bars, and also modeling the behavior, the nonlinear behavior of the isolator. Here you can see where the building is working, no? So as I mentioned to you, this is, for example, how the building will behave without an isolation system, and this is how the same building will behave during an isolation system. So it will move like a rigid block. And here you can see, depending on the properties of the isolators, because as I mentioned to you, the isolator, the characteristics of the isolator are not fixed. They can change because they are affected by many factors. Depending on the type of properties that I consider, the nominal properties, the lower properties, and the upper properties, you can see where I am in terms of spectral acceleration, and where I would be if the structure is not isolated. So here, for example, we can see in this slide, we can see, for example, the floor displacement of the isolated building. So you can see that the building is behaving like a rigid block. All the displacement is concentrated up at the bottom, and on the bottom you can see the story drift. So the story drift is always very low. I think that we never exceed the 0.01 drift ratio, no? During the whole earthquake. And this is because the structure is behaving like a rigid block. So then, once we finish to perform the seismic analysis, then we can take a look to the hysteretic response of the isolator. So thanks to a time history analysis, this is the typical response that you get. Here you can see the force displacement response of an isolator for each time history analysis that was performed. And finally, with the red line, we have the average of all the response, while the green light, that is this one, is the response that we get with the approximate method. That could be, for example, the response spectrum analysis. This is for the longitudinal direction, and this is for the transversal direction. As expected, the time history analysis is a more complex analysis, and therefore the advantage is that the response is less conservative. While if I perform, let's say, an approximate analysis, the advantage is that I will find a response of the isolator that is more conservative. In other words, I will find a higher shear force and a higher displacement of the isolator. In fact, if we combine the maximum displacement of the two analyses, so the response spectrum method, that is the green line, and the time histories method, that is the red line, we can see, for example, that with the time history analysis, I get, in upper bound condition, I get a displacement of almost 200 millimeters. While with the time history analysis in upper bound condition, I get a reduction up to 144 millimeters. Then, for example, according to Ash, I need to amplify this displacement by 15% to take into account the torsional effect of the device. And so in the end, I get a displacement of 165 millimeters. That is almost minus 50% of the displacement of the approximate response spectrum analysis. I can do the same for the transversal direction. Again, if I perform the time history analysis, you can see that I'm able to reduce the displacement of the isolator. Let's say that the American standard for buildings, ASHE, allows for a maximum reduction of the displacement of 20%. So you can understand that is an important reduction. So the standard is saying to you that if you perform a time history analysis, you can reduce the displacement of the isolator up to 20%. And finally, if we take a look, and this is very important, the concept of seismic isolation, why for this project, we have modeled all the beams and columns with their real nonlinear behavior of concrete or steel. The reason was to verify that during each time history, for example, if we take a look here we have the moment curvature of a typical column of the building. So why let's say we introduced the full nonlinear model of the building? Because we want to demonstrate that during each time history analysis, for example, the behavior of each column, it's linear. So we are always in the elastic range. In fact, for example, this is the moment curvature response of a column. These are the different performance limit states of the column. So this is for this level of curvature, plus minus, we are in the elastic range. Then we have the immediate occupancy limit state, life safety limit state. And we can see that actually for almost all the time history, the maximum performance level of the column, it's always elastic. And only in two time history, the time history 5 and time history 11, we are a bit exceeding the elastic ranges. We are a bit entering in the immediate occupancy limit state. Here, for example, but then let's say if you perform at least 6 time history analysis, then the standard tells you that you can take the average response of all the time history. So in the end, we have verified that the response of all the structural elements is completely elastic. In fact, if, for example, we take a look to the stress-strain curve of a steel bar in the column, for all the time history, we can see that actually we are in the elastic range. As well as if we take a look to the stress-strain curve of a confined fiber and of an unconfined fiber, again, we can see that the concrete is almost in the linear range. So we have reached the goal of an isolated structure. The main goal of an isolated structure is that during an earthquake, during the design earthquake, we don't have any damage on the structural elements. Again, if we perform a time history analysis, for example, we can take one isolator and, for example, we can take a look to the vertical reaction of the isolator. Again, this is very important because, for example, the rubber isolators compared to the friction isolator, they have a certain tension resistance, but anyway, this tension resistance is very low. So with the time history analysis, we can see exactly for each time history what is the variation of the vertical load. And for example, as you can see here in this table, for each time history, we can take the maximum peak, the maximum compression, let's say the maximum positive and the minimum, the maximum and the minimum value for each time history. And as I mentioned to you, if we perform at least 6 time history analysis, the standard allows us to take the average of the peaks as a design parameter. So in this case, for the design of this isolator, we will have to consider a maximum compression load of close to 900 kilonewton and a minimum compression load of 17 kilonewton. So going to the conclusion of this example, and this is also the conclusion of the presentation, what we can say, this is a conclusion that is valid in general for isolated structure. In this case, it was a building. The first conclusion is that a seismic isolation system is a very effective system that can protect both new and existing structure. I didn't mention that seismic isolation can be implemented also in existing structures. And also this protection strategy let's say, indicates that we can have a better and enhanced structural performance. Why? Because during an earthquake, the superstructure will essentially behave elastically. The second point is that, as I mentioned at the beginning of the presentation, we will not have any damage during the earthquake, so we will not have any future repair cost implicated after an earthquake event. We can use the importance factor 1 for all risk category, because if the structure is isolated, we can reach the same level of performance independently of the importance of the structure. And this indicates that we can have, this comes from statistics, we can have a probable initial cost-efficient solution, especially for structures that are in risk category 3 and 4. So this means that if I have to design a structure of risk category 3 and 4, so it means hospital, bridges, the advantage that I can have by isolating the structure could be very important. It could be from 25 to 50% higher if I design the structure conventionally. And also another important point is that a seismically isolated structure cannot be compared directly with a conventional design building, or in other words, with a ductile system. Why? First of all, because if I design an isolated structure, or if I design the same structure with a ductile behavior, I need to expect different performance level, first of all. Second point, I am designing the structure with different level of earthquakes. In fact, if I design my structure isolated, the structure is designed elastically, so to behave elastically for the maximum, up to the maximum considerable earthquake. The typical is the 2,500 years return period. If I design the same structure non-isolated, now what I do is to design the structure for the life safety for typically 2/3 of the maximum considerable earthquake. So that's why when we compare a seismic isolated building with a conventional building, we have to take into account that, okay, one building is ductile, the other building has the isolator, but we have also to remember that we are designing the two structures with two different levels of performance. So we need to pay attention when comparing different design strategy. So with this slide, I have finished, unfortunately, a bit in delay my presentation. And so now let's see if we have some question in the chat. I think yes. Okay, useful life we answer. What could be the estimated cost of maintenance of this type of system and periodicity of maintenance? Thanks, Luis, for this question. It's an interesting question. Well, typically, let's say the seismic isolators, seismic device. So I mean isolators and dampers. They are supplied with let's say an inspection and maintenance manual. But think about that it's more an inspection than a maintenance. So typically you have an inspection manual, and with a specific program. For example, if I remember well, for rubber isolator, you have like 5 inspections in the first 5 years from the installation, where you have to inspect the isolator to check if there could be some defect, if you could have some let's say corrosion in some part of the isolator. So thanks to this regular inspection, that is again a visual inspection, you can monitor the isolator and check that everything is okay. But it's more an inspection, so it's not really a maintenance. It's an inspection that has to be done in a specific moment. It is suggested to do it after an earthquake to check that everything worked properly. But if after this inspection everything is okay, actually there is no maintenance. Of course, if you inspect an isolator after 20 years, it could happen that, for example, there was a problem of corrosion, and in that case, it could be necessary maybe to replace, let's say, an element of the isolator. So it's more, let's say, an inspection activity that is mandatory. For us, it's mandatory for the first 5 years from the installation. After these 5 years, we suggest the client to agree a new inspection program, maybe more delayed in the time, to continue, let's say, the inspection of the isolators all over the year. There are softwares, also Luis is asking, there are softwares for designing or calculating this type of systems. Well, the thing is that the design of the isolators as a product is, let's say, an activity that is done by the manufacturer. In fact, when you, let's say, buy an isolator, when the client buy an isolator, we produce the isolator and we also submit a technical package where you have, the calculation note, all the checks, all the calculations of the isolator. So let's say there are no software that can, let's say, calculate the isolator, meaning calculate all the elements of the isolator, because in the end, the designer is interested in the global performance of the isolator, the stiffness, the damping, the displacement capacity, the vertical capacity. But the design of the components of the isolator, this is done by the manufacturer, and this is demonstrated by calculation reports and by the testing of the real device. We have 2 questions from Carlos Fernandez. What are the disadvantages of using isolation devices in places where the ground is soft? First question, well, yes, of course, think about that when we introduce a seismic isolation, as I mentioned, we increase the period of vibration. So, of course, what does it mean this? It means that we need to have a soil, or in other words, we need to have a spectrum where if I increase the period, I decrease the acceleration. To answer to your question, if I have a very bad soil where by increasing the period, I increase the acceleration, of course, seismic isolation is not a good strategy. So in that case, maybe you can introduce damping instead of isolating. So having the shape of the spectrum, we can understand which strategy is better. It's like the example that I show you with the simple frame. Could you comment useful life of the devices? As I mentioned before, we go from minimum of 40 to maximum of 60 years, depending on the product and depending on the environmental condition. Do you have knowledge about the variation of the mechanical properties of the devices over time? Yes, the answer is absolutely yes. Not because we are, let's say, Fressinet, we are a manufacturer, but it is mandatory. It is mandatory to know for each product, so rubber isolator, friction isolator, damper, how these properties will change over the time. So for each product, we are able to tell you what is the range of variation for different sources of variation of the parameters, so that the designer can take into account the variation in the software. Francisco say, hello Stefano, thank you for your presentation. We have 2 bridges here in Costa Rica that have shock transmitters to the abutments, and they have never received maintenance since 2000 approximately. How long do they last lifespan, and how they are affected by dust or dirt? Well, good question, Francisco. I will tell you that since 20, so it means that it's almost 24 years that they are not inspected. So without any inspection, for example, one of the problems that you could have with a shock transmission unit or with a fluid damper could be the lack of the fluid, because it could be a defect of the device, no? So the inspection is also to check this, because if you have some lack of the fluid, you can immediately see it with an inspection. You can immediately understand if it is if the device has to be replaced, or if it is just a problem of the dust protection that has to be changed. Of course, if you do not inspect the device for 20 years, I cannot tell you what is the situation, because after 20 years there could be also problem of corrosion in the cylinder or in the spherical hinge. So inspection is really important, because it's a way to monitor the device, and if let's say a problem will occur, we can immediately take an action. Could the bridge behavior be affected by the lack of maintenance? They are accompanied with pot bearings, which are also heavily corroded. Some of them have lost their oil reservoir. Yes, Francisco, if you tell this, of course, let's say the behavior of the bridge as a whole system can be drastically affected, because if you are saying that the shock transmission unit has lost the oil, it means that, in other words, during an earthquake or during a breaking load, because it depends if the shock transmission unit is used to, let's say, for breaking load, or sometimes it is used for wind load, sometimes it is used for earthquakes. But if you don't have any oil, it means, in other words, that the device cannot react during the dynamic event, so it will move. So the deck will not be locked, so it will move during the breaking load or the earthquake action, and this could create problem, because, for example, the deck could crash could hammer against the abutment. So this is really, I would say, an issue. And if you are sure about this, I suggest to ask the contractor of the bridge to call to make a sort of tender or to ask a manufacturer. For example, as Fressinet, we do this activity, and we do the activity of inspecting devices. For example, for the Panama Canal Bridge, we inspected the fluid damper from other competitors. So the inspection is an important activity because if the device is not, you understand that the behavior of the structure is in some way governed by the device. So if the device is not working properly, the whole structure will not work properly. And the same for the pot bearings. If the pot bearings, imagine that the pot bearing has typically a level of grease, lubrication between the sliding plate and the sliding material. Of course, if you don't monitor the bearing and, for example, the lubrication is expired, this means that the pot bearing will behave with a friction of, I don't know, 10% instead of 1%. And this means a completely different behavior. It could be conservative or not. It has to be analyzed, but for sure, the behavior of the structure is affected, will be affected by the variation of the products. In the case of concrete structures, the idea is to maintain the elastic structure. Yes, also for steel structure, for example, the concept is to keep the behavior elastically. In terms of detailing or ductility, under what criteria should be columns or beams be detailed? Just to maintain elastic? Exactly, Juan Pablo, exactly. For example, in the Eurocode, the Italian standard, but I think it's the same in the American standard, if you design the isolated structure and your superstructure is elastic, you don't have to follow all the rules of detailing that are necessary when you design a structure for ductility. So you can simply use let's say, the rules for elastic elements. You don't have to follow any additional criteria, let's say, for the design. Okay, I think that, yes, I think that we answered to all the questions. So I don't know if there are other comments, curiosity.
Okay, in that case, Stefano, thank you so much for your time, for all the information you provide to us. I think all the participants can reach out in the future in case of they have more questions.
Yeah, sure. The idea, let's say, of this webinar was to give you, let's say, a sort of overview, no, of what is this technology, how it can be implemented. But then, of course, as you said, if some of the engineers, students, if they are interested in specific topics, in specific arguments, we can, of course, we are available for discussion. We are, as Facilitador, we are also more than happy to, for example, invite students, for example, to do their, their thesis or their, let's say, stage period in our company, because you have the possibility to work in the laboratory, to, let's say, to see the whole. Fortunately, we have all this process internal, so you have the possibility to work in the design department or to work in the laboratory. So we are more than happy to collaborate with students or with their thesis work. If, for example, they want to implement a particular isolator in their software, and maybe they want to perform analysis with the more advanced behavior of the isolators. We have all the experimental results, so we can also provide more detailed characteristics, in order to perform advanced analysis and to compare, for example, with respect to basic analysis. So for all these type of activities, feel free to reach Farlin. That is actually our contact for both Costa Rica and Panama, and so we will be more than happy to support you.
Okay, thank you so much again for your time.
Yeah.
I think this is the end of the activity. Hopefully, there will be another one in the future. Thank you so much.
Yeah. For example, one thing that I just mentioned and then I conclude is, for example, the retrofit of structures, especially buildings with seismic isolation. I can tell you that in countries like in Italy, in Turkey, in Romania, for example, this is becoming the most important trend. So the seismic protection of existing structure, because we are an old continent, so we deal with many old buildings that were designed with no seismic code. So seismic isolation can be also implemented in existing buildings, and there are different techniques in order to implement it. So, for example, one idea could be to organize in the future, next year, a specific training, a specific seminar on how to implement seismic isolation in existing structures. And again, it will be a seminar, let's say, how can I say, a seminar like a presentation like this, where you will not see, let's say, Fresine in the slide, because it will be a conceptual training, conceptual material that the students, the engineer can use, whatever is the, let's say, the supplier that they will contact in the future.
Sounds great. Okay, thank you so much again. See you soon then.
Yes, thank you. Have a nice day. Bye.